All right, so this is the video for gravitation and spring forces. By just getting to this video, you probably went through the course schedule that had all the links to everything. Right next to the link to this video will be a link to the practice problems. So the link to the practice problems, I'll also link this hopefully in the video description where the video is posted. But make sure you have those practice problems up and ready to go. Just work on these on a separate sheet of paper wherever you take your notes. All right, so gravitation and spring forces. We have to go through these two more kinds of forces, just two less kinds of forces. You might be wondering right now, gravitation, well, haven't we already learned about gravitation? Okay, to an extent we have, right? Force of gravity we've learned equals mg, but that's on planet Earth. What happens if we go to a different planet? Well, at a different planet, G is different. G is different for different planets. And there's no way for us to really, figure that out. So, or to figure out what G is, there is a way for us to figure out what G is, but there's no way to really know it or have it memorized for every single planet. What we do is we give ourselves a way to calculate it. Basically, here's our setup. Okay, let's say we have two planets. Let's say one's bigger than the other. Let's say this one has a mass of m1, this one has a mass of m2. Then let's say that the distance between the center of these planets, and that is a very important fact, from the center of these planets is a distance of r. Okay. Then the force of gravity between these two planets, we'll still notate it as F sub g. Force of gravity is equal to this. Capital G is a gravitational constant times m1, m2 over r squared. That's our equation for the force of gravity. So G is it's called the universal gravitation constant. G is equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared is the units on it. That is on your equation sheet. You will never have to memorize that. That's always on your equation sheet. I will always give it to you anytime you need it. So this is just a constant G times the mass of the first planet times the mass of the second planet divided by the distance between them squared. All right, and that's how we calculate the force of gravity between any two, I'll call them planetary or interstellar objects. Basically, all that means is that things the size of a planet, or at least things that, just don't exist on the planet. All right, so if you get to our practice problems here, you will notice that equation is given to you right there. F sub g, g mm over r squared, where g, acceleration of g, the universal gravitation constant, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. All right, we'll get to the spring forces later. We'll get to that later. For right now, let's just take a look at some gravitation problems. So I've got 4 gravitation problems here. Take a look at these first few. So these first few, I'll do 3 at a time. Just copy these 3. So let's come over here and scroll to the top of this page. Here we go. Okay. So first question I'm going to ask you here. What is the force of gravity between the sun and the earth? Okay, force of gravity between the sun and the earth. I'll make this just a little bit smaller. On this, okay, I'm asking what's the force of gravity? That means we're solving for F sub g equals question mark. Now, normally you would just say equals mg, right? However, these are planetary or stellar objects. These are big space things. Whenever we have big space things, little g, the acceleration of gravity, does not apply. All right, little g, this is only on Earth's surface. Earth's surface. That's it. That is it. This happens on Earth's surface only. Anytime we're not talking about the surface of Earth, we cannot use little g as 9.8. We cannot use that, or as 10, depending on how we're rounding. Whenever we're talking about like something, the sun and the earth, we don't care about the surface of the earth at all. So we have to use this gravitation law. So F sub g is g m1 m2 over r squared. Okay. So I tell you here, F sub g equals, well, g we know that is 6.67 times 10 to the negative 11. Mass 1, we can choose the mass of either of these to put first. Let's say the sun. So 2 times 10 to the 30th. And then mass 2, well, we have just the Earth left. So 6 times 10 to the 24. Okay, there's g, m1, m2. And then divided by r squared. So r, 1.5 times 10 to the 11th meters. But it's over r squared, so that gets squared. Okay, so there's our equation there. All that's left for us to do is plug it into the calculator. Okay, so on our calculator, yes, you could say on all these, you could do something like 6.67 times 10 to the negative 11. You could type that, but that's a lot of work, right? For every single number. Instead, what we'll do, we can do 6.67, this little EE right here, this capital EE that's on the second function of the comma. Hopefully you remember this from previous classes, but second EE, that means times 10 to the. So this capital E means times 10 to the. So if I do 6.67, E means times 10 to the negative 11. That gives me this 6.67 times 10 to the negative 11. So when I'm typing all these over here, I'm actually, because I just like to write things quickly, I'm a little lazy sometimes, 6.67, instead of writing times 10 to the negative 11, what I will typically do, I will usually write E minus 11. This means 6.67 times 10 to the negative 11. And then over here for the mass of the sun, 2, E means times 10 to the 30. And then for the mass of the earth, 6, E 24. That means 6 times 10 to the 24th. And then I'll do divided by 1.5 E 11 squared. And what's nice, two things. One, I can write this very quickly. I don't have to write a bunch of little numbers and the exponents up here. But the other thing that's really nice is this is exactly how we will type it into our calculator. So if we come back to the calculator here, we can do 6.67 E, means times 10 to the minus 11, and it's to the negative 11, times 2 E 30, so there's the mass of the sun, times 6 E 24, there's mass of the earth, and then divided by the radius squared. So divided by 1.5 E 11, but that number gets squared. I now hit enter. There we go. So the gravitational force between these two is now going to be 3.5. If we do 3 sig figs, that runs up 3.56. E means times 10 to the 22. So we got 3.56 E, so times 10 to the 22. And this is a force of gravity, so units of newtons. Okay. Just make sure I got that number right. 3.56 times 10 to the 22nd newtons. Perfect. That is our acceleration, or sorry, not our acceleration, our force of gravity between the Earth and the sun. That's a lot of apples, right? 3.56 times 10 to the 22nd. What that number actually is, that is 3 and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. That is that many newtons. So million, billion, trillion, quadrillion, pentillion, hexillion, 35 hexillion Newtons. A lot of newtons. All right. So that's the force between the Earth and the sun. Well, that's a huge force, but it's acting on a huge object, right? So I'm going to ask now, what is the acceleration of the Earth due to this force? So since it's just due to this force, that means when we write the sum of the forces, it's just going to be this force of gravity between the sun and the Earth. And I'm asking about the acceleration of the Earth. Acceleration of the Earth means I'm just going to consider the mass of the Earth. So mass of the Earth is 6e24. The Earth and the Sun, they honestly have pretty nice masses to do calculations with. So mass of the Earth, 6 times 10 to the 24th kilograms. I'm looking for what's the acceleration of the Earth due to this force between them. So 3.56 times 10 to the 22nd newtons. Okay, so we'll just take both sides, divide by 6e24, divide by 6e24. Okay, those cancel out. So this tells us that our acceleration of the Earth due to this force, let's see, 3.56 times 10 to the 22nd divided by 6 times 10 to the 24th gives us 0.00593. 0.00593. It's an acceleration, so meters per second squared. Okay, so that's the acceleration of the Earth as it moves around the sun. Excuse me. Let's contrast this with the acceleration of the sun. So just like when a semi-truck hits a little car, the little car is going to go flying because it has got a tiny mass. Well, in this case, relative to the Earth, the sun is basically the semi-truck. So the Earth goes flying because it's got a tiny mass. Not tiny, but compared to the sun. So let's find out exactly how much. This will be the sum of the forces acting on the sun. The previous problem, it was the Earth. That's going to equal mass times acceleration of the sun, which is, right, this is just, it's Newton's third law. If the sun exerts a gravitational force on the Earth, then the Earth exerts a gravitational force on the sun. So it's going to be the same exact force. Same exact force. With the mass of the sun, if you look up in the problem, we were given 2 times 10 to the 30th kilograms. So 2 times 10 to the 30th kilograms. We'll solve for the acceleration of the sun equals, and it's the same force between them thanks to Newton's third law. Newton's third law makes our life pretty easy. So times 10 to the 22nd. And you'll notice I go back and forth between E and times 10 to the, they mean the exact same thing. So E22 means the exact same thing to write it either direction. So now we'll just divide by 2e30 to get acceleration on its own. Divide by 2 times 10 to the 30th. All right, this tells us acceleration of the sun. Okay, 3.56 times 10 to the 22nd divided by 2 times 10 to the 30th. 1.78 times 10 to the negative 8. So times 10 to the negative 8, it's an acceleration, so meters per second squared. Okay, so this one, if we did scientific notation, would be 5.93 times 10 to the negative third. This is times 10 to the negative 8th. So a tiny, tiny, tiny number. This basically just shows us, all right, well, the sun and the Earth exert gravitational forces on each other. It's the same force because of Newton's third law. However, the Earth has got a small mass, relatively speaking, so a much bigger acceleration because the sun is a huge mass, so it has a tiny acceleration. All right. Then we've got one more practice problem down here, I believe. One more practice problem. Yes, so let's copy and paste this, grab it over to the drawing program, and I love that little ding dong it makes. Okay, here we go. So the elliptical orbit of Nereid, that's how you say this. This is Neptune's third largest moon, is very non-centered. It gets as close to Neptune as 1.38 times 10 to the ninth meters, and as far away as 9.36 times 10 to the ninth meters. I'm going to give you the mass of Nereid and the mass of Neptune. How many times bigger is the force of gravity when Nereid is closest to Neptune than when it's at its farthest? Okay. Basically what this problem is, Neptune, I always feel like Neptune's blue, right? We'll do Neptune as blue. Neptune, I guess they both start with N. And then Nereid feels like a green moon to me. What this means, the elliptical orbit of Nereid. Everything in space orbits at an ellipse, at an elliptical pattern. So it's not a circle, right? We would expect, and kind of our expectation is that it's a circle. It's a pretty good circle. Pretend like that's a perfect circle. That's our expectation, but that's not actually, that's not how it works. I could have probably drawn this a little bit better or a little more easy to erase. It's not how it works. It is not, this is not a circular orbit. Instead, what Nereid will do is Nereid will make an elliptical orbit around Neptune like this. We'll learn more about this later, but basically over here, because it's really close. So it gets as close to Neptune as this. So that's going to be over on this side. But then as far away as this. So that's going to be way when it's over here. So far away, right, it's not going to have as good of a hold on it. It's not as big of a gravitational force. Okay. We'll learn more about this later in something called Kepler's laws. But for right now, let's just do some calculations. So we're going to calculate when it's at its closest and when it's at its furthest. Okay. So when it is at its closest, well, let's just find the force of gravity between Nereid and Neptune when it's at its closest. Okay, so this is going to be, right, G mass of, and I'll call this Neptune, times the mass of Nereid divided by radius when they're close squared. So force of gravity when they're closest as compared to when they're the farthest away. So we can do the force of gravity when they're furthest, right? It's G M1, which is Neptune, M2, which is Nereid, over R squared. But this is R when they're far squared. Okay, all we've got to do now is just plug in some numbers. Let's plug in some numbers. Okay, so when we're over here, right, G 6.67 times 10 to the minus 11. As always, you will be given that on your equation sheet. You can find that on your equation sheet. Okay, then the mass of Neptune, I tell you, is 1 times 10 to the 26. Mass of Nereid, 3.1 times 10 to the 19. And then the radius when they're close together, okay, it gets as close as 1.38 times 10 to the 9th meters, but that gets squared. Okay, so if we get our calculator, let's plug the calculator. I'll try to get it over here. Okay, plug this calculator in with these numbers. 6.67 times 10 to the negative 11 times 1 times 10 to the 26 times 3.1 times 10 to the 19 divided by 1.38 times 10 to the 9th, but that gets squared. All right, there we go. 1.09 times 10 to the 17th. 1.09 times 10 to the, all right, times 10 to the 17th is a force, so newtons. Okay, so that's when it's closest. By the way, this scientific notation, I will almost always use times 10 to the when reporting my answer, because the AP test, it goes back and forth, but sometimes the AP test just does not accept this E notation. The AP test must have the times 10 to the. They're totally fine with you doing all your calculations in E notation, but when you give your final answer, you have to do times 10 to the. You have to write it all out. Okay. Yeah, that's just a nuance about AP. I don't get it. I don't understand it, but we do have to live with it. So there it is. Okay. So that's when narrative is at its closest. Let's now find out when narrative is at its farthest. What's the force? Okay, so this is actually, it's going to be the same exact numerator, right? G, 6.67 times 10 to the minus 11. Mass of Neptune, 1 times 10 to the 26. Mass of Nereid, 3.1 times 10 to the 19. Divided by 1.38. No, I'm sorry. This is the new radius. This is now the radius when they're farthest away. Radius when they're furthest away, which is 9.63. 9.63 times 10 to the 9th meters, but that gets squared over r squared. Okay, so if we plug this in with our calculator, I'm just going to hit second, enter. You see how this little entry right there in blue, that means if you hit second enter, that gives us the new entry. Because I don't want to retype the whole top if I don't have to. So if I just now use my left arrow over here, because instead of this 1.38 times 10 to the 9th business over here, instead of this 1.38 times 10 to the 9th, because that's the only thing that's changed, it's now 9.63. So by using the second enter, it repeats my entire entry, but now I'm just going to go in and type over this 9.63, and it's still times 10 to the 9th. So I can just hit enter. It spits out my new number for me. So 2.23 times 10 to the 15th. 2.23 times 10 to the 15th. And you'll notice it's in scientific notation because it's the answer, and AP just has their weird random rules. All right. There we go. So now we know the force when it's at its closest and the force when it's at its furthest. Well, I ask you, how many times bigger is the force at its closest than at the furthest? So basically all we just need to do, we need to take the force at the closest divided by the force at the furthest. So 1.09 E17, divide that by 2.23 E15. If we get that, this should give us some number here. I'm just going to take this and go up, hit enter, divided by, and then this one, enter, 48.7. 48.7 times greater. That is our answer. All right. So there we go. There's numbers 1 through 4. There's numbers 1 through 4 of these questions here. So that should take us through gravitation and only leave us with springs. That'll take us through gravitation. However, I found this while scrolling through all my nerdy Instagram pages that I followed the other day, because that's all my Instagram is full of, is just nerd pages that make me laugh. So here we go. When the moon attracts her more than you do. This guy did a gravitational force calculation of the moon. So GMM over R squared. So the moon's attracting her, right? So this is the mass of this guy's love interest, and then this is the mass of the moon. So, right, we have G and then M1, M2 over That's the distance from the Earth's surface to the center of the moon, which we would assume is the distance from the center of the girl to the center of the moon. So times 10 to the 8th meters. That spits out this. But now, if we just do, okay, let's say that we're 2 meters away. All right, we're following these 6-foot COVID protocols, right? 60 kilograms for her, 78 kilograms for him. 6.67 times 10 to the minus 11, right? That's G. So GMM over R squared. And this is why you get their crying meme. Because the moon has a times 10 to the minus 3, but you have a times 10 to the minus 8. So yes, your moon will attract your crush more than you attract them gravitationally. But hey, here's the good news. You still attract your crush gravitationally. So regardless of how small of a number that is, you still attract them. That's what gives me hope in this world. All right. So we are going to now go on to springs. Springs. If you scroll up to the top of our gravitation and spring video problems, you'll notice this equation right here. So force of a spring is just equal to K times delta X. K times delta X. What that means? Let's say we have a spring attached to a wall, right? Every spring, if we don't do anything to it, it has an equilibrium position. So let's say we have a box at an equilibrium position. But now let's say we take this box on the spring and we pull it out. We pull this box out, right? So the spring's wanting to snap back that way. We are pulling it that way. So this is the spring force is wanting to snap back in to get to where it was at rest before. But we are pulling it. Let's say we're just doing a tension force over that way. We're pulling it that way. The spring's pulling it this way. Well, our question is, how much is this spring force? So we got that equation. Force of a spring is equal to K delta X. I'll come back to this K variable in a moment. But this delta X, all right, I'm just going to track how far we've moved this box. Just whatever the displacement is, we call this the equilibrium position. Equilibrium, assuming my pen wants to actually write equilibrium. We call this the equilibrium position. That means when the spring is not exerting a force. So spring's not exerting a force at delta X equals 0. But over here, we've stretched the spring. So the spring wants to pull us back. This is, whatever distance this is, that's our delta X. And it must be in meters. Must be in meters. Much like everything else. I will typically give you this in terms of centimeters, but you have to convert this to meters. So let's say it says 2.0 centimeters. You would have to take this and say, oh, okay, so that's 0.02 meters. Then you would use this number in your calculation. All right, so there's delta X, but what about this? What about this K value here? This K is something we call our spring constant. K is called the spring constant. This spring constant is given in units are newtons per meter. Essentially what that means is if we were to draw a graph of our spring force and our delta X, the slope of this graph, this tells us, so our spring force and delta X. This means that as we pull it more, the force increases. If I were to pull it even further, the force would get even bigger. Pull it even further, the force gets even bigger. This is our linear relationship, our direct relationship. So as delta X increases, so does the spring force. So does the spring force. The spring constant is given in units of newtons, right? Spring force is in units of newtons, and then delta X is in meters, so of newtons per meter. Basically, this is the excuse me, this is the slope of that graph. It's rise over run, newtons per meter. That's where spring constant comes from. So the further you pull it, the more force you have to pull with. And it turns out that it's a linear relationship. Okay, so this newtons per meter for our spring force, it can be anywhere from, right, we've got our cheap little flimsy springs like our slinkies. Those have got about like a 10 newtons per meter. 10 newtons per meter. It's not very much. 10 newtons, that means you pull 10 apples for every meter that you stretch the spring. However, then you get things like a car shock. A car shock, those are huge springs. So this is what lets your wheel bounce up and down without the rest of your car moving. Those are huge springs with very high spring constants. So you can have a spring constant anywhere from like 10 newtons per meter, that's like a slinky, to like 5,000, maybe even 50,000 newtons per meter, because you have to pull with so many newtons to stretch the spring out by 1 meter. That's what these units mean, is you pull by 50,000 newtons to stretch the spring 1 meter. Or on a slinky, maybe you pull 10 newtons to stretch it out for 1 meter. That's what that number means. All right, so now let's use this equation. Force of a spring equals K delta X. Let's use this equation to solve some of these problems. Okay, so I'll copy over these first two here. Copy these first two. Okay. A nice little copy sound. All right. So spring has a spring constant of 92 newtons per meter. Okay. K equals 92 newtons per meter. If the spring is stretched 2.5 centimeters, okay, here's what I warned you about centimeters. I'm just going to change this right now, 0.025 meters. Spring is stretched 2.5 centimeters from equilibrium. What is the force of the spring? All right, this whole phrase right here, 2.5 centimeters from equilibrium. This from equilibrium tells us that this is delta x. So delta x equals, and then right, we always need meters, so we converted this to 0.025 meters. Well, we've got our relationship right here. Okay, force of the spring equals K delta X, which means force of a spring, plug in K, 92. Plug in delta X, 0.025. All right, our spring force. Let's bring this over here, 92. Let's get a calculator on. 92 times 0.025. We get 2.3. 2.3. This is a force, so units of newtons. Boom, just that easy. Just that easy. That's it. All right. Next question. A person compresses a spring. Ooh, compresses. Okay, so that's something interesting as well. So you see this equilibrium position here. We've got just a random block being held by a spring to a wall. Right, that's the equilibrium position, is along this line. But what happens if I take this block, let's say I get my hand right here, and I push that way? Well, if I push that way, that means that my spring is going to be really compressed now. So the spring force is going to push back. Spring force will always push toward this equilibrium position because the box wants to be in the equilibrium position, but I brought it over here by using a pushing force. So the spring force is going to try to return it to this equilibrium. So this just tells us that whatever this delta x is, this is delta x. And then the spring constant has some k, or the spring is some constant of k. This also works not only for pulling a box out, it also works if we push a box in and compress the spring. Okay, so if we compress a spring by 5 centimeters, okay, you see 5 centimeters, immediately I want you to say 0.05 meters. Okay, they compress a spring by 5 centimeters, holding with a force of 64 newtons. What is the spring constant of the spring? Okay, well, this one There's now two forces, so they're holding with the force of 64 newtons, just like the picture we just drew. So this tells us that they're pushing in with a force of 64 newtons, but the spring force is pushing back out. So we can either say holding, right? That holding means it's at rest, so acceleration is 0 meters per second squared. So we could do our sum of the forces is ma is force of the spring minus 64, but our acceleration is 0. So force of spring equals 64 newtons. Jumped back a couple pages on me. 64 newtons. Force of the spring is 64 newtons. Okay, but what is force of the spring also equal to? K delta x. We are looking for what is the spring constant of the spring. So K equals question mark. We need that. So let's substitute in our delta x. Well, how much did we compress the spring? By 0.05 meters. So we've got 64 newtons is equal to K times 0.05 meters. Oh, goodness. Here we go. 0.05. So all we have to do to get K, divide both sides by 0.05, divide by 0.05. These cancel out. So our K is equal to, let's see, 64 divided by 0.05, 1280. So 1,280 K, spring constant, units of newtons per meter. You got to remember that. Units of newtons per meter. All right. So there's a couple of those questions there. Let's come back and grab the last two questions here. Last two questions. I'll work through these kind of quickly. I know this video is going on a little bit longer, so I'll work through them kind of quickly here. All right. Okay. Oh, my computer just went dark on me. I wonder if it's given up. Okay, so let's try to do these quickly, just in case my computer does give up. 3.2 kilogram box is at rest, hanging from a spring. What is the spring force? Okay, so this tells us we've got a spring force up, but force of gravity down, force of gravity. This time we are on Earth's surface, so we can just say mg 32 newtons because a 3.2 kilogram box. So this tells us what is the spring force? Well, spring force has to equal our force of gravity because it's being held in place, 32 newtons. Boom. Okay, but if the spring constant K is 240 newtons per meter, how much is the spring stretched? Gosh, there's a lot of tongue twisters in these spring problems. Remember, force of spring is K delta X. So we know this is 32 newtons. We know K is 240. So we just have this delta X left. Divide both sides by 240. Divide by 240. Delta X is equal to 32 divided by 240. Let's figure out what that is. 32 over 240. 0.133. 0. Oh, it's given up on me again. 0.133. X is in units of meters. All right. So that's how much it's stretched. Last problem. Okay, 2,200 kilogram car sits at rest on 4 wheels. Each wheel is held by the car shock and suspension, and the car shocks have a spring constant each of 180,000 newtons per meter. Okay, so I guess I misestimated earlier when I said cars would have a smaller. I said 50,000-ish maybe, but 180,000 because I remember doing my research when writing this problem, so that's a more accurate number. So 180,000 newtons per meter. How much is each spring compressed when the car is stationary? Okay, I'm going to attempt to draw a terrible picture here. Just utterly miserable, except for our driver is smiling. All right. But then we've got wheel, we've got wheel. What happens here is each of these wheels is set up to a shock. If you look if you look underneath your car, you'll notice that each wheel is set up to a shock or this big spring. These are the ones that I've drawn for the wheels on the other side that we can't see. So it says that rest on 4 wheels, which means there's 4 springs. Okay, so 4 wheels, 4 springs. This means that if we draw our free body diagram, we've got 1, 2, 3, 4. All of this is force of spring, but there's 4 of them. And then down, force of gravity. So this tells us that since it's at rest, our force of gravity, right, it's just mg, so 22,000 is equal to 4 times whatever the spring force is. Divide both sides by 4, divide both sides by 4. This should, 22,000 divided by 4, 5,500. So 5,500 is our spring force. But what is our spring force also equal to? Oh, that's right, K delta X. So we know K, 5,500. We know K is 180,000 delta X. So all I do, divide by 180,000, divide by 180,000. This leaves us with delta X. Okay, 5,500 divided by 180,000. Make sure, yep, that's the right number of zeros. There we go, 0.0306. So 0.0306. This is delta X, so it's in meters. If you really wanted, you can convert this to, say, 3.06 centimeters, but it's just an equivalent number. All right. If you have any questions, please do let me know. Otherwise, I will let you go. I know it's a slightly longer video, but if you have any questions, let me know. Have a great rest of your night. I'll see you in class next time.